Hi everybody, welcome to another lesson, and today we're going to be talking about double integrals over rectangular regions. Now when we look at these double integrals over these rectangular regions, what we want to do is we kind of want to recall a topic that we learned back in Calc 1. Oops, excuse me here. So we're going to go back to recall a topic that we dealt with back in Calc 1. That topic being that we can have an integral from a to b for some function f of x dx, and this will be equal to the limit as n goes to infinity for the summation of I beginning at 1, stopping at n, for your function evaluated at some random sample point, and we account for the changes by dx. Now we're going to be using this definition to elaborate a little bit more as to what these double integrals look like. Alright, so as far as we're going to be concerned, we're always going to be operating on closed rectangular regions for this section. And these closed rectangular regions look like this. Oops. Typically it's denoted by r, and then we give one interval. The first interval is from a to b, and then we're going to cross it with another interval moving from c to d. So when we're looking at this particular piece, this here is your x interval, and this here is your y interval. And because this is a case, we can write this in set builder notation. Set builder notation is just going to say that all of the ordered pairs x, y are in some R space 2, and we're defining the x values to be bounded between a and b, and the y values to be bounded between c and d. Alright, and that's exactly what I had elaborated here. Now we're going to define one more thing. And that last thing that we're going to define is that we want to identify some solid. Alright, I'm going to say this is going to be the solid that lies above the region R. And this is going to be classified as S. And this is going to be the surface that is made up of all of these triple coordinates that exists in R space 3, such that the function output is positive, or at least greater than 0. And that's going to be for the z coordinates. And then in this particular case, x and y, well, they already belong in R space 2. Alright, so given this, we now want to elaborate, and we want to now start building this definition for a double integral. Once we've identified, hey, we have some closed rectangular region, that's going to act as our quote-unquote domain, alright? And then everything else, meaning all of the z values, are going to be bounded by some function that we're going to be looking for. And that's then going to create some solid. Alright, and that's what we want to pay attention to. Alright, so really quickly, let's start viewing this under a depiction for a drawing. Alright, so follow me along here. I'm going to start making my axis. Alright, now I'm going to put pause on the video and I'm going to magically appear this. I'm going to make this axis magically appear, so bear with me. Alright, so we're back. Now, here's my x and y axes. Alright, now according to what we have for what we defined here, we're supposed to have some closed rectangular region that is going to be defined on this x and y plane. And that's where we start. Alright, we want to start by analyzing what is our A, what is our B, what is our C, what is our D. Alright, so I'm going to go through here really quickly and I'm going to start identifying that. Alright, I will start at some value for A. some value here for A, and then I'm going to keep going a certain amount so that I can get to B. But trying to forecast ahead, I kind of want to make sure that I start partitioning this kind of evenly so that I can go back and I can rely on this definition here back from Calc 1 where we had our dx, or in this case our delta x, which was our even partitioning. Alright, so here I have A, so I'm going to go on over and I'm going to have my next value, and then my next value, so on and so forth. You know what, I'm going to make them a little bit larger just for this particular purpose. Alright, and here's my even partition. So I'm going to call this first one x0, and then this one's going to be x1, then this one's going to be x2, and we're going to be able to keep going all the way forward. Alright, so this one will be x3, and then what we'll do is we'll skip a few, we'll go to our x sub I, and we'll skip a few again, and then we'll go all the way to, let's say, x sub n minus 1, and then we'll go to x sub n. And stopping at x sub n, this is going to be the equivalent of stopping at b. And so one of the reasons I'm doing this is so that I can then start identifying what is my delta x and what is my delta y, so on and so forth. So for this particular piece of information here, we have that our delta x is going to be given by b minus a divided by n, where n is going to be the amount of subdivisions that we want. Alright, nice. So now that we got this set up, I want to do the exact same thing for the y values. I want to go through and I want to start subdividing the y values, kind of like what we did here from C to D. So taking this interval and just subdividing it. Now, because we're going to make these subdivisions rectangular regions, that means that the subdivision for the x values does not need to be the same as the subdivision for the y values. Alright, so we're going to go ahead and we're going to, let's say, get started on there. And let's say that we start here on C. Here we are. All right. So if we start here on C, we're going to call this y naught. There we are. And then this is going to be y sub 1. And then we can keep on increasing y sub 2, y sub 3, so on and so forth. All right. But in the interest to make this not the same, I'm going to say not the same subdivisions. I'm going to go with this is y sub j. All right. Not y sub I, because this could be a different index. All right. And then this is going to be y sub, and I'm going to choose here to be m minus 1. And then this last value here, the last value is going to be the value of d, which is y sub m. All right, perfect. So now we got all these subdivisions set. And the subdivision that we chose for the y values, that was our delta y, to be equal to this d minus c divided by m. And again, m is just that subdivision for the y values. Perfect. Now what I want to do is I want to start creating my rectangle here. Alright, so I'm going to go through and I'm going to start creating this rectangle that I can now start observing. Oops, sorry. Let's go here. Now I'm telling you, if I was trying to do this in class, it would take me a little while as well to try to generate all these pictures to the best of the ability that we can in the classroom. Right? Now, I do have GeoGebra examples, and I want to show you those GeoGebra examples. But again, first I want to make sure that we go through the process of creating these rectangular regions. That way we can see how these rectangular regions were developed, and then using GeoGebra we can then see how we're going to talk about them and how we're going to keep using them to our advantage moving forward through the rest of the semester. There we are. Perfect. All right, so now we have this rectangular region that we are now looking at. And this rectangular region, again, this came about because we started saying, hey, let's define some rectangular region, and then let's start with some random subdivisions. All right. Now, one of the things that I'm going to ask you all is this. If I wanted to find this area for that rectangle, what would the area for that rectangle be? Well, according to the process of the area of rectangles, it's just length times width, right? Or base times height. But notice that area here, well, that distance we defined as delta x. This distance here we defined as delta y. Which means, could we just say this is just some delta x times some delta y? Sure we can. That's exactly what we then start observing. All right. So that's something that we then want to consider, is that any time that we take any area within this rectangular region, any area will always be looking like delta A. Delta A is just going to be composed of delta x times delta y, and that's just going to be the change in the area that we want to observe, where delta A is going to be dependent on which subdivisions we choose for n and m. Awesome. So now what I want you to do is I want you to try to visualize what's happening here, all right, and what's happening here in just a little bit. All right, so now that we've identified that we have this rectangular region, we've subdivided this rectangular region, now what we want to do is we want to use this last piece of information that we haven't used that says that we have some solid that lies above that region that we were looking at. So imagine this here, rectangular region, being that domain that we are now observing. Some three-dimensional function, or some function that exists in R space 3, is going to, by our definition, sit above the x and y plane. So I want you now to imagine this. Take this area in orange here, and I want you to figuratively pull this area up to some function. That area that you will be, quote-unquote, pulling up is going to generate a rectangular figure in 3 dimensions. All right, it's going to be this rectangular box. I want to show you what that is on GeoGebra. So follow me along to GeoGebra. Here we are. So I have some rectangular region here. All right, so here's my rectangular region, has 4 subdivisions along the x-axis, has 3 subdivisions along the y-axis. Now I have some function embedded on this, all right, and the function is over here on the left. All right, that's 5 minus x squared divided by 2 minus y squared divided by 4. So that in itself is an elliptic paraboloid. So when we're looking at this elliptic paraboloid, we're going to look at this domain and we're going to imagine pulling all of these individual rectangles up to this function. What does that look like now? Let's show the function here. There we are. So each individual rectangle was pulled up to that specific height of the function. Again, that creates this rectangular box in R space 3. One thing that we know about rectangular boxes in R space 3 is that we can generate a volume from that. So the big question is now, can we take all of these individual rectangles then and start calculating each individual volume? That's the next question. Interesting. All right. Now, as you probably guessed, the higher that you go with your subdivisions, here we go. The higher that you go with your subdivisions, look what this is doing. This is actually creating a very good approximation of the volume that exists underneath this surface, but its constraint is the X and Y plane. All right. So very similar to that definition that we got back in Calc 1 that said, hey, we can talk about some area of some function made underneath the function and the x-axis. Well, we're doing the same thing here, except now it's in R space 3. All right, so let's go back and let's finalize this. Awesome. So now that we're here, what I want to do is I want to go through and I just want to create some random sample point. All right, so let's pick some random sample point. Let's say we pick the sample point here. All right, what I'm going to do is I'm going to label this sample point x sub I star and y sub j star. Perfect. Now, according to this, if I want to find the area here, all right, so the area for the rectangle containing x sub I star and y sub j star is, again, just delta A by our previous work right up here. And again, I want a random sample point just so that we're staying ambiguous here. It doesn't matter where we choose a sample point, the result is always going to be the same. That's why we label this as x sub I star and y sub j star. The star just means that they're randomly selected on this particular rectangular region. All right, so if we now wanted to calculate the volume made by the rectangle that contains x sub I star, y sub j star, and the height, and this is going to be the height that we're going to be looking for, and it's going to contain the height that goes up to the surface. The height of, I'm going to say S star. S star is just going to be the function that's going to be evaluated for that surface given this particular point. All right, so in order to calculate that volume, now this is going to be nice because the volume for a rectangular region is just length times width times height. Or in other words, area multiplied by height. So if this is just area multiplied by height, all I need to do is figure out what the height is. But under the assumptions that we're working with here, the height is just going to be S star. But S star, that's just the function evaluated at the sample point, which makes it a little bit easier to work with. All right, so this now actually provides us the volume. This provides us the volume for, again, the rectangle that contains the sample point and gives us a height of that surface. Awesome. But again, that's only one rectangle. So what if I want to do all of these rectangles? So not just this one. I want 1, 2, 3, 4, 5, 6, and then 6 times 4, 24. I want all these 24 rectangles to give me a good approximation. All right. Now, if I want a good approximation for, if I want a good approximation for this rectangular region that is going to approximate the volume, well then what I'm going to start looking at is this particular piece. All right, let's see. We're going to say that the volume of the rectangle region and the surface S is approximated this is going to be approximated by taking the summation of all of the I values and all of the j values. J's, again, we subdivided those to stop at m, and the i's we subdivided to stop at n. And we want to make sure that we add up all of these individual function outputs. That way we can get each individual height for these functions. And we want to multiply them by the individual areas, which they'll all be delta A. And again, this gives us a good approximation for the volume. But again, in the business of calculus, we're not in the business of approximating. We want a firm value. We want an exact value. So how could we get away how can we get away with not approximating? Well, the way we do that is by this definition back in Calc 1. We operated using the Riemann sum, and that's exactly what we did. We found this double Riemann sum. So this double Riemann sum's taking place. All we now have to do is take all of these individual n and m values and just subdivide them infinitely. So, can we get a firm approximation or a firm exact value? Yeah, the answer is yes. So this is going to tell us that the volume that we're going to be looking for is the limit as n and m both go to infinity, and that's for the summation of I beginning at 1, stopping at n, j beginning at 1, stopping at m, for the function evaluated at all of the individual sample points multiplied by delta A. This leads us into the definition for the double integral. The double integral then said, hey, this was integrating, double integral, over some general region R, because that's where all of our rectangles were then subdivided in. And we evaluated all of these rectangles at some height that was denoted by your actual function, and that was here. And this was all with respect to the changing area. Well, integral-wise, we just call that dA. And this here, ladies and gentlemen, is that definition for a double integral. This is your double Riemann sum integral that we work with. All right, so awesome. So now we see where this was developed, how this was developed, and now we can start going through some of these examples. All right, so bear with me. Now, when we work with double integrals, and we have them look like this, where this goes from a to b, and then from c to d, and then we use f of x, y. We evaluate this working from the inside out. And again, these are known as iterated integrals. When we want to work with the first iteration of the integral with respect to dy in this particular case, and then after we work with this, then we work with dx. All right, so again, we work from the inside out. Now let's check out this example here. So we want to evaluate this integral from 2 to 3, then from -1 to 1, for 16xy minus 9x squared plus 1, and this is going to be dy dx. All right, so again, we're going to work from the inside out. That's from 2 to 3, and then we're going to work with the first integral here from -1 to 1, and this is going to be for 16xy minus 9x squared plus 1, and this is all dy. Now again, the whole purpose for us going through this whole process of partial derivatives is so that when we get to this part of double integrals, we get to play on the fact that an integral is just an antiderivative, and so what we then just have to do is we then have to find what is the antiderivative of this function with respect to y. That means every single x component or every constant then just gets treated as such, which is a constant. So when we integrate the innermost integral gets integrated with respect to y. So 16xy, I treat the x as a constant and I only integrate y. So y, the integral of y is just y squared divided by 2. But 2 is going to divide 16, so that's going to leave us 8x y squared. And again, you can take the derivative. If we take the derivative, that's going to be 16xy, which is this piece. Integrating this with respect to y, that's going to get us 9x squared, and then we multiply by y. And then plus integrating the constant of 1 with respect to y is just y. And then we evaluate this from -1 to 1. And again, we're only evaluating the y components. We're not evaluating anything else at this time. So we're going to go through and we're going to evaluate that function with respect to 1 and -1. So it's going to be 8x times 1 squared plus 9x squared times 1 plus 1 minus 8x y squared, that's at -1, minus 9x squared times -1 plus -1. There we are, and this is all still going to be dx. And this is the integral from 2 to 3. Let's see what we're left with. Alright, here we're going to be left with 8x. Here is 9x squared, that's negative. And then we're left with a plus 1. And then this is going to be a minus. So it's going to be minus 8x. There we are. Negative is going to distribute, so negative times a negative gets us a positive, but then this negative is going to make it a negative again. So that's minus 9x squared. And then this here, negative times a negative, is just going to be a positive. There we are. And that's all dx. We're left with the integral from 2 to 3. Let's see now. 8x cancels out with 8x, and then we're going to be left with negative 18 x squared plus 2. And that's dx. Excuse me. Now all we have to do then is integrate this particular function here with respect to dx. So this now just turns into a Calc 1 problem, which is really nice because, again, at this point in time, we can just say, okay, well, from Calc 1, that's going to be real nice here. So that's going to be what? Negative 6x cubed, right? 6 times 3 get us that 18. And then plus 2x evaluated from 2 to 3. This is negative 6 times 3 cubed plus 2 times 3. minus, that's going to be negative 6 times 2 cubed plus 2 times 2. There we are. All right. And then all we're going to go through is we're going to go through and evaluate all this. All right. So 3 cubed, that should get us 27, times 6, that should get us that negative 162. Nice. And then we're going to get plus 6. Then here, again, 2 cubed. So 2 cubed, that's going to get us 8. And then 8 times 6, that should get us 48. Negative times a negative is going to be positive, so that's going to be plus 48. And then negative in here, so it's going to be negative 4. So then all we have to do here is just go through and add everything. So 48 plus 6 minus 4 minus 162, that should get us negative 112. And that's the final answer. All right, now the big question here, all right, the big question. Looking at this particular integral that we were given, because the bounds here are both numerical, they're both numerical bounds, this is a rectangular region. The y values went through negative 1 to 1. The x values went from 2 to 3. So again, it made a rectangular region. Now, according to rectangular regions, we could do base times height or length times width. Does it really matter if it's dy dx or if it's dx dy to calculate the area? And the answer should be no, it doesn't matter, right? Which means at this point in time, does it matter how we structure our integrals? Meaning, could we have set this up in this manner? Negative 1 to 1, and then 2 to 3. 16xy minus 9x squared plus 1, and the innermost integral goes from 2 to 3, but 2 to 3 corresponds with dx. So could we have then set it up this way? The answer is yes. Yes, we can definitely set it up that way. Now, we can set it up that way specifically because we have one awesome theorem. And this is known as Fubini's theorem. I love that name, Fubini. Sounds very magical. All right, so Fubini's theorem. Now, Fubini's theorem says if you have a continuous function on some rectangular region, we'll just classify this from A to B and then from C to D. Sorry guys, my computer is acting kind of funky right now. There we go. From C to D. Then the double integral over that region for the function f of x, y with respect to the area can be set up as the integral from a to b and then from c to d for this function with respect to, and actually let's not make this dA, let's actually make this with respect to the innermost is dy and then dx, or we can set it up the integral from c to d, the integral from a to b for this function f of x, y. The innermost was the x values, so that's dx, the outermost were the dy's. Alright, so depending on how we want to set up this integral, if it's a rectangular region, we can use Fubini's theorem. Using Fubini's theorem just allows us to change the order of integration. If we want to integrate with respect to x, awesome, then we'll do that. If we want to integrate with respect to y, awesome, then we'll do that first. Alright, so however it is that we want to do it, we then just have to pay attention to those bounds in order for us to proceed. Alright, now let's go ahead and let's calculate some double integrals. Alright, so here we have the double integral over some region R for the function x squared y squared plus cosine of pi x plus sine of pi y. And this is all going to be with respect to some area. And the region in question is a region from -2 to -1. And then we're going to cross this region with 0 to 1. Now again, every time they give us a region in this form, the first interval is always your x interval, and then the second interval is always going to be your y interval. Alright, so because this is a rectangular region, and we know it's a rectangular region because of the bounds that they give us. Since it's a rectangular region, what I want to do is I can use Fubini's theorem to say we can integrate with respect to x or with respect to y first. Doesn't matter. Alright, so however it is that you want to set it up, that's perfectly fine. I'm going to go through and set up my x's here, -2 to -1, and then I'll do the y's, which is going to be from 0 to 1. This is x squared, y squared, plus cosine of pi x, plus sine of pi y. And then my differentials, from 0 to 1, that's my y's. And then after that is going to be my dx's, because that's the interval that was associated with it. So, iterated integral, we're going to work with the innermost first, and we're going to make sure that we find the antiderivative for this function with respect to y first. So let's see, with respect to y, this is now going to be 1/3 x squared y cubed, again keeping the x's constant, because we're only integrating with respect to y. This is a constant because it's cosine of pi x, and we're differentiating with respect to y. Sorry, or we're trying to find the antiderivative with respect to y, which means this is just going to be y times cosine of pi x. And it's y because, again, this was treated as a constant. Plus, antiderivative for sine is cosine. But the cosine function here has an embedded chain rule that we need to account for, so we just use a substitution, and that would be that 1 over pi. But then, if you recall, this should not be a positive, this should be a negative. Because if we then take the derivative of -1 over pi cosine of pi y, derivative of negative cosine is just sine. Chain rule would differentiate the inner, which means pi times 1 over pi, which would get us a constant of 1. Awesome. And we're going to evaluate all this from 0 to 1, and this is all just dx. So let's look at this. -2 to -1. Alright, I'm going to evaluate with 1, and again, I'm only evaluating my y's, not my x's. So this is 1/3 x squared multiplied by 1 cubed plus 1 times cosine of pi x minus 1 over pi times cosine of pi times 1. Now, I do have the option here because we're going to evaluate at 0. Let's go through and let's see. Alright, this piece at 0 is going to cancel. Alright, and I'm actually going to show it. I was debating on not showing it, but I think I'll show it talking about it. Here we go. Minus 0 times cosine of pi x, and then that's going to be a positive because the minus distributes, so what's 1 over pi times cosine of pi times 0. Alright, and then after that, that's going to be the dx. So let's simplify before we find the antiderivative. Because when we simplify, everything's going to look kind of nice. So this is going to be 1/3 x squared plus cosine of pi x. There we are. Cosine at pi. So all we then have to do is figure out what cosine at pi is. Well, cosine at pi, that should be -1. Alright, awesome. So this is going to be plus 1 over pi, because again this is cosine of pi. Nice. This goes to 0, This goes to 0, and then we're left with cosine at 0. Cosine at 0, let's see what we get there. Cosine at 0, we should just get 1. Nice. So that's just going to be 1 over pi. And this is all still dx. Looks pretty good so far. So let's keep going then. Now that we have our constants set, -2 to -1, we now have 1/3 x squared, and this is going to be plus cosine of pi x, and this is now plus 2 over pi. It's looking real good. That's dx. Let's integrate with respect to dx now. So integrating with respect to dx, all right, this is now going to be, what was that, 1/9 x to the power of 3. This is now going to be plus 1 over pi sine of pi x plus 2 over pi multiplied by x, evaluated from -2 to -1. All right, let's go through. That's going to be 1/9, -1 to the power of 3 plus 1 over pi times sine. This is going to be multiplied by -1, so I'm just going to write it in as negative pi minus 2 pi because it's evaluated at -1, and then subtract out the rest. So subtract out, let's evaluate this, so that's going to be 8 over 9, and if I subtract it out, it's actually going to make it a positive because -2 cubed is -8, so -8 times that minus, when we subtract it because of the integral, gets us 8/9. All right, and then we subtract because of the integral here, so that's going to be minus 1 over pi sine of -2 pi. All right, it's looking good. Then minus and minus, so that's going to be a plus, and that's going to be 4 pi. 4 over pi. There we go. All right, it's looking good so far. All right, now sine of 2 pi, can we all agree that's just 0? Sine of pi, hey, look at that. Or sine of -pi, that's just going to be 0 as well. All right, so that's not too bad. All right, so let's see what we have here. We're going to have -1/9. We're going to have plus 8/9. And I believe for those constants, that's it. And then we have -2 pi. Sorry, -2 over pi plus 4 over pi. All right, this should get us a really nice answer of 7/9 plus 2 over pi. Nice. There is our answer. So again, we all started with this iterated integral. And what I want to make sure for you all is that as we keep going through this course, just keep making sure if you're not solid with your integration techniques, meaning partial fraction decomposition techniques, U substitution, integration by parts, trigonometric substitution, any substitutions that you've covered before, if you are not too, let's say, solid with them, I want you to make sure you go through and you try to review them as you're going through the course. All right, let's look at part B. Alright, so here's the example for part B. So we want to work through this example, and I see some x values here. That is kind of nice. I think I might want to do this with respect to y first, but again, at the end of the day, it doesn't matter because our bounds here are rectangular bounds, and since it's rectangular bounds, Fubini's theorem will apply. Now, I like to be different a lot of times, and so in the previous problem we set it up as dy dx, so in this problem I'm going to set it dx dy. So dx is going to go first. That's going to be -1 to 2. And that's going to be dx. There we are. And the next one is going to be y. Like such. All right, nice. Now, if we start looking at this and say, okay, well, maybe could we make some substitution and could we work with it? Yes, that might be an option. However, I'm going to caution you with that because looking at this option here, dx kind of implies that we're going to have to use by parts here. All right, so I kind of want to keep that in my back pocket, is that I might be using by parts here, and by parts I'm going to have this one variable that I then need to treat as a constant, which is going to make it a little bit more tough. So just by that quick analysis, I think I want to change my limits of integration to be this. Just like that. Now, if I change my limits of integration just like this, then I can focus on my y's first and go through the whole process, because then all the x's are just constants. All right, well, let's see. If it's now a constant, or if all of my x's are now constants, this is a constant, this is a constant, which means I'm just integrating e to the power of xy, but x is a constant. So when I do this, this is now going to leave me with e to the power of xy. All right, looking good so far. And this is all evaluated from 0 to 1 dx. Now, if we take the derivative here, the derivative of e to the xy is just e to the xy itself, but then since we differentiate with respect to dy, we multiply by this derivative. The derivative of x times y with respect to y should just be x itself, and that's what we multiply by. All right, now having this here, this makes it slightly easier in the sense that, again, I'm only evaluating y's, so this is going to be e to the power of x times 1 minus e to the power of x times 0, and that's all dx. This is e to the x minus 1. All right, and this is all dx. Now, this turns into a pretty straightforward integration. Let's go through. All right, so e to the x, find that integral, that's just e to the x, minus integrate 1, that's just going to be x, evaluated from -1 to 2. So this is going to be e to the power of 2 minus 2 minus e to the power of -1 plus minus 1. There we are. Which means our final result is just e to the power of 2 minus e to the power of -1 minus 3. That's our final answer. Now, if we wanted to do this integration first, all right, the one that I initially set up, this one, we would need to use by parts. Now, if you want to use by parts, by all means, go ahead. Feel free to use by parts. But again, if there's a way around it, let's try to work with that way around it. Awesome. So, good stuff so far. Now, let's see what's going to happen if we can try to, let's say, change out our integrals. All right, because there's something that we want to work on, or there's something that we want to observe that will make things, or that will make integrals a little bit easier to evaluate. All right, and this is what I'm going to call your separation of your function. All right, so here we go. So if your function f of xy can be split into two different functions where each function contains their own separate variables, and we can integrate, or sorry, and we are integrating so we're integrating over the the rectangle R, which goes from A to B, and then cross C to D. Then the double integral over that region for that function f of x, y with respect to dA can be thought of as a double integral over the region where we have that function being split. And this is all dA. What we can do, since a function is separable and each individual portion of the function does not contain the other variable, what we can do then is we can integrate here, let's say from a to b, for my first function g of x with respect to dx, and we can multiply that by the function evaluated from c to d for the variables containing y's, just like this. This process doesn't happen often, but when it does, it is useful. And it is useful because, again, if we can separate our integrand into a separable function, then we can naturally separate the integrals over that function as well. Alright, so we got to be careful when we're doing this because, again, it'll make things easier to work with. Let's see. Calculate the double integral. Oops. I spelled integral incorrectly. There we go. Alright, part A. We're going to be looking for the double integral over the region of tangent of theta divided by the square root of 1 minus t squared. And that's going to be with respect to dA. And this is going to be where the region, we are defining this to be all the ordered pairs theta comma t such that theta is bounded between 0 and pi thirds, and t is going to be bounded between 0 and 1/2. Alright, so let's go through it. Can we then separate? Or, you know what, let's backtrack. Do we have a rectangular region first? Yes. So we have a rectangular region, which means we can apply Fubini's theorem. Doesn't matter which variable we integrate with respect to first. We could integrate with respect to theta, or we can integrate with respect to t first. Fubini's theorem allows us that choice. Now, is the function separable? Can we separate that function? Alright, so that's the next question. Can we then separate it? Could we then write it as tangent of theta multiplied by 1 over square root of 1 minus t squared? Could we do it this way? That's a big question. And the answer is yes. So the function is separable. Alright, that's one of the first pieces. Great. Function is separable, and it's also a rectangular region, which means we can go through and we can set it up in this manner. So if we can set it up in that manner, we can just go to the thetas. Thetas are evaluated from 0 to pi thirds, and that's going to be just tangent of theta d theta. Then we're going to go over to the next integral, which is going to be from 0 to 1/2, and that's just going to be 1 over the square root of 1 minus t squared, and that's dt. Nice. Not bad. Not bad at all. Alright, so now I want you to keep going. Oops. You're going to have to keep going from here. I'm not going to give you the answer from here. Instead, you're going to have to input your answer onto Canvas. Alright, so you're going to have to put in the answer in the discussion board for the class. Alright, so let's go with part B. Integral from 0 to 1 and then integral from 0 to 2. And this is going to be for the function y times e to the power of x minus y, and this is dx dy. So first, is it a rectangular region? Yes. Awesome. It is a rectangular region. Next, is the function separable? Can I separate this function into two different functions that contain x's and y's? Well, let's see. We have this piece. If you remember your pieces of information from, let's say, algebra, it turns out that if we add in the exponents, we can multiply in their bases. So naturally, can we then separate? Let's see, 0 to 1 was y's. Looks like this, dy. And then we have the integral from 0 to 2, and that's e to the x dx. So the answer is yes, we can separate, but then what's the answer? Well, guess what you have to do? You have to keep going. And this is actually where I'm going to end the lesson for today, that we can do this, and what I want you all to do is I want you to finish these two integrals. All right, I want you to finish these two integrals and see what you get. All right, I'm going to be looking for the answer on the discussion board. So I hope you all enjoyed this lesson, and I'll see you all next time.